Welcome to G Fun Facts Online. Today, we are looking up, way up. We are exploring the engineering marvels that define our skyline and our history. For as long as humanity has looked at the stars, we have felt a need to build things that reach for them. From the sands of Egypt to the riverbanks of modern India, our species has spent millennia crafting colossal human figures that defy gravity, logic, and often the economy. These are not just statues. They are engineering miracles and tests of pure ambition. But how do you build a 600-foot human out of bronze and steel? How do you keep it standing when a typhoon hits? And why are we building them taller than ever before? Today we are discussing the story of sculpting giants. To understand the modern titans, we have to look at the impossible builders of the past. The most famous mega-statue of antiquity is the Colossus of Rhodes. Erected around 280 BC, it was a bronze statue of the sun god Helios, standing about 108 feet tall. That is roughly the height of the internal skeleton of the Statue of Liberty. For centuries, medieval art depicted the Colossus straddling the harbor entrance with ships passing between its legs. However, modern engineering tells us this was impossible. The structural stress on the groin area would have caused it to snap under its own weight instantly. In reality, the Colossus likely stood on a pedestal near the harbor. The construction method was pure genius born of war. The people of Rhodes melted down the bronze and iron from abandoned Macedonian siege engines, towers, and weapons left behind after a failed invasion to build their god. It was literally made from the recycled weapons of their enemies. The engineered chairs of Lindos built it in horizontal sections, riveting bronze plates to an iron framework and filling the hollow interior with stone blocks for stability. It stood for only 54 years before an earthquake snapped it at the knees. While Rhodes crumbled, the Great Sphinx of Giza endured because it was carved directly from limestone bedrock, a process of subtraction rather than addition. Its survival was largely due to geology, as it spent thousands of years buried up to its neck in sand, protected from erosion. But the game changed forever in the late 19th century in a workshop in Paris. When Frederick Auguste Bartholdi designed the Statue of Liberty, he faced a physics problem. He wanted a figure of copper, but copper is soft and heavy. A hollow copper statue of that size would collapse like a crushed soda can. He needed a skeleton. He turned to Gustave Eiffel. Before Eiffel built his famous tower, he designed the internal spine of Lady Liberty. He created a central iron pylon backbone with a web of lighter bars reaching out to hold the copper skin. The engineering breakthrough here was the connection. The copper skin is not rigidly fixed to the iron frame. Instead, it floats on saddles. This allows the skin to expand and contract with the heat of the New York sun without cracking. This technique is known as curtain wall construction, and it is the same principle used in almost every modern skyscraper today. Liberty was the prototype. In the 21st century, the race for height has accelerated. We are no longer satisfied with 100 feet. We are pushing past 500. The current king of the world is the Statue of Unity in India. Standing at a staggering 182 meters or 597 feet, it is nearly twice the height of the Statue of Liberty. Located in Gujarat, it depicts Sardar Vallabhbhai Patel. The engineering challenge here was immense. Unlike a pyramid, a human figure is aerodynamically a nightmare. It has broad shoulders and narrow feet, making it naturally unstable. To keep it upright, engineers used two massive reinforced concrete cores that house high-speed elevators to act as the spine. But the real enemy of the Statue of Unity is the wind. It is located in a river basin subject to high winds of up to 180 kilometers per hour. To manage this, the statue has two tuned mass dampers. These are massive 250-ton weights suspended inside the chest area. When the wind pushes the statue one way, these weights swing the other way, canceling out the vibration. This is the same technology used in buildings like Taipei 101. Then, there is the Garuda Wisnu Kencana in Bali, Indonesia. This is perhaps the most complex statue ever built. It depicts the Hindu god Wisnu riding the mythical eagle Garuda. It is not a simple standing cylinder. It has a mass of wings, feathers, and flowing robes with a massive wingspan of 64 meters. Because of those wings, the statue acts like a giant sail. Engineers had to test scale models in wind tunnels in Canada to ensure the tropical storms of Bali would not tear it apart. It was built in 754 separate modules, cut into pieces, transported by truck and ferry, and then welded back together like a giant three-dimensional jigsaw puzzle in the sky. We also have to mention the Motherland Calls in Russia. Completed in 1967, this 85-meter statue depicts a woman stepping forward with a sword raised. The engineering here is terrifying. The original stainless steel sword was so heavy and caught so much wind that it caused the statue to sway dangerously. It had to be replaced with a perforated structure to let wind pass through. Even more concerning is the foundation. The statue is not fixed to the bedrock. It stands on its base, solely by its own weight, floating on a clay foundation. Rising groundwater has caused the clay to shift, leading to a leaning tower situation that has required millions of dollars in reinforcement to prevent it from toppling over. Building a mega statue involves overcoming three primary enemies of physics. Enemy number one is the square cube law. As you scale an object up, its weight grows much faster than its surface area. If you double the height of a statue, it becomes 8 times as heavy. This is why you cannot simply scale up a classic sculpture like Michelangelo's David. His ankles would shatter instantly under the multiplied weight. Modern statues require high-strength reinforced concrete cores just to support their own crushing mass. Enemy number two is vortex shedding. When wind hits a cylindrical object like a statue's arm, it flows around it and creates alternating swirls on the backside. This creates a rhythmic push-pull force. If this rhythm matches the statue's natural sway frequency, the statue can resonate and shake itself apart, similar to a singer breaking a wine glass with their voice. This is why wind tunnel testing and tuned mass dampers are non-negotiable. Enemy number three is thermal expansion. Metal expands when hot. A 182-meter statue might grow by several centimeters on a hot day. If the skin were bolted tightly to the rigid concrete core, the statue would rip itself apart. The solution is the floating skin method, pioneered by Eiffel, allowing the metal to breathe and slide without transferring stress to the skeleton. Finally, we have to talk about the economics and the cost. Why do we build them? It is a mix of piety, politics, and profit. The Statue of Unity attracted over 2.9 million visitors in its first year, generating roughly $11 million and transforming the local region into a tourism hub. However, the economic success is not guaranteed. The Ushiku Daibutsu in Japan sees steady visitation, but hasn't revolutionized its regional economy in the same way. These projects are also enormously expensive. The Statue of Unity cost over $400 million, and the Garuda Wisnu Kankana took 28 years and over $100 million to finish. There is also a dark side. The construction of the Statue of Unity used 210,000 cubic meters of cement and concrete. Since cement production is responsible for a significant portion of global carbon emissions, building a mega statue is essentially a massive carbon bomb. Furthermore, these projects often displace local communities and reshape natural landscapes. Looking to the future, the race might be slowing down. The proposed Shiv Smarak in Mumbai, planned to be taller than the Statue of Unity, has been stalled by environmental litigation and cost concerns. We are reaching the limits of what is economically sensible. Future monuments might be dynamic kinetic sculptures that move with the wind, or digital colossi made of drone swarms that create 1,000-foot figures without pouring a drop of concrete. But whether made of stone, steel, or light, the drive remains the same. We build them because we are small, and the universe is large. Standing at the foot of a giant, looking up at a face the size of a tennis court, provides a primal sense of awe. And as long as humans can feel awe, we will keep building giants. Thanks for listening to G Fun Facts Online.